lot of what we do is modeling and studying the noise, says Cornish. And you know, honestly, you guys, I wish I could apply my Snipes analogy to this paragraph here, but it's just so damn complex and convoluted. I probably could, but I just don't want to spend the time on it. I think you kind of get what they're saying here, but it is just a load of malarkey, my man. Just a load of malarkey. Anyway, quote, the paper on the first detection used a data plot that was more illustrative than precise. Jackson is suspicious of LIGO's noise analysis. Go Jackson. Isn't that what scientists are supposed to do? Be suspicious of things and double-check things? Yay. Gold star for Mr. Jackson. And I'm sorry, Miss Jackson. Woo! I am for real. Anyway, one of the problems is that there is no independent check on the collaboration's results. That wasn't so with the other standout physics discovery of recent years, the Higgs boson. The particle's existence was confirmed by analyzing multiple, well-controlled particle collisions in two different detectors at CERN near Geneva, Switzerland. Both detector teams kept their results from each other until the analysis was complete. Or did they? I question everything. That's a whole other can of worms. We're not going to go into Higgs boson and CERN just yet, maybe in another video. But at any rate, by contrast, LIGO must work with single, uncontrollable, unrepeatable events. Although there are 3 detectors, they work almost as one instrument. And despite there being 4 data analysis teams, they cannot work entirely separately because part of the detection process involves checking that all the instruments saw the signal. It creates a situation in which each positive observation is an uncheckable conclusion. Outsiders have to trust that LIGO is doing its job properly. Let me just read that last sentence again. Outsiders have to trust that LIGO is doing its job properly. And when it comes to theoretical science guys, you know, these guys who are getting just millions and millions of dollars to do, well, fuck all as far as I'm concerned, we have to trust that they're doing their job properly. And by the way, they named their multi-billion-dollar lie factory LIGO. So at least they're honest about one thing, right? Yeah. Purely illustrative. And there are legitimate questions about that trust. New Scientist has learned, and New Scientist is this website that we're reading from here, that we're sourcing here. New Scientist has learned, for instance, that the collaboration decided to publish data plots that were not derived from actual analysis. The paper on the first detection in Physical Review Letters used a data plot that was more illustrative than precise, says Cornish. Some of the results presented in that paper were not found using analysis algorithms, but were done by eyeball? What? Say what? I mean, come on, you guys. I don't even think when you go down to the local dispensary and buy a quarter-ounce of pot, they do that by eyeball. And that's just grows on trees, and it's legal in many states. Brown, part of the LIGO collaboration at the time, explains this is an attempt to provide a visual aid. It was hand-tuned for pedagogical purposes. He says he regrets that the figure wasn't labeled to point this out. And in case you were wondering, pedagogical, it means relating to teaching, which, embarrassingly enough, never heard that word before today, so wow, we really are increasing our useless vocabulary today, aren't we, you guys? Pedagogical. Ask me to remember that word tomorrow, and I will probably not. So it was hand-tuned for teaching purposes. He says he regrets that the figure wasn't labeled to point this out. So it was labeled as if it was fact, but it was more along the lines of just to maybe make a point or to teach, right? It's the way I'm reading it. Maybe I'm wrong, but hey, pedagogical. There you have it. So this presentation of hand-tuned and eyeball data in a peer-reviewed scientific report like this is certainly unusual, and I would call it just downright fraud, but hey, who am I? I'm still trying to find snipes out here. New Scientist asked the editor who handled the paper, Robert Garisto, whether he was aware that the published data plots weren't derived directly from LIGO's data, but were pedagogical and done by eyeball, and whether the journal generally accepts illustrative figures. Garisto declined to comment. So, just a quick point here, you guys. Everybody who has all the kerfuffle about peer-reviewed this and peer-reviewed that, well, LIGO, the multi-billion-dollar lie factory, does things by eye sometimes, just wild guesses sometimes, and sometimes they put things in there just for pedagogical purposes. Didn't you know? Okay. There was also questionable shortcuts in the data LIGO released for public use. The collaboration approximated the subtraction of the Livingston signal from the Hanford one, leaving correlations in the data. The very correlations Jackson noticed. There is now a note on the data release webpage stating that the publicly available waveform, quote, was not tuned to precisely remove the signal. Wow, well, isn't that just something? Jeez, what are these guys doing, man? Hey, can we have their budget and explore south? I'd really love to know what's out there, you guys. Give us LIGO's budget and a couple of years, man. I guarantee you we'll come up with some just fascinating stuff that'll be actually tangibly worth a damn to humanity in the future. Promise. Guarantee it. Anyways, back to the article. Whatever the shortcomings of the reporting and the data release, Cornish insists that the actual analysis was done with processing tools that took years to develop and significant computing power to implement, and it worked perfectly. However, anyone outside the collaboration has to take his word for that. That's problematic. And you know what? It even says so in the article. Quote, it's problematic. There's not enough data to do the analysis independently, says Jackson. It looks like they're being open without being open at all. Remind you of anyone? I'm not going to say any names, but NASA. I'll go ahead and read that last bit again. Again, this is Andrew Jackson, quote, it looks like they're being open without being open at all. Wow. Brown agrees that there's a problem. Quote, LIGO has taken great strides and are moving towards open data and reproducible science, he says, but I don't think they're quite there yet. So if they're not doing reproducible science, then what the crap are they doing out there in their multi-billion-dollar lie factory? I would love to know, and so would many other taxpayers, I'm very sure. Do you want uppies, baby? Come on, hold on. Come on, I'll put you uppies. Come on, 1, 2, all right, there you go. Don't steal my seat. Don't steal my seat. That's my seat. Seat thief. You're such a little seat thief, Bubas. Good God. Okay. The Danish group's independent checks, published in 3 peer-reviewed papers, found that there was little evidence for the presence of gravitational waves in the September 2015 signal. On a scale from certain at 1 to definitely not there at 0, Jackson says the analysis puts the probability of the first detection being from an event involving black holes with the properties claimed by LIGO at 0.000004. That is roughly the same as the odds that your eventual cause of death will be a comet or asteroid strike directly hitting you, or, as Jackson puts it, pretty damn consistent with 0. The probability of the signal being due to a merger of any sort of black holes is not huge either. Jackson and his colleagues calculate it as 0.008. But this is proof of gravity, isn't it, globetards? Oh, sure it is. And monkeys might fly out of my butt. Alright. Simultaneous signal. There is other evidence to suggest that at least one of the later detections came from a gravitational wave. which of course, gravitational waves do not exist, but we're going along with this article because at least these guys have one thing going for them. They don't have their heads completely up their butt so far that the little lump in their throat is their nose, right? So at least they don't have that. On 17th of August 2017, right before the Great American Eclipse, no less, the orbiting Fermi telescope saw a burst of electromagnetic radiation at the same time as the LIGO and Virgo detectors picked up a signal. Analysis of all the evidence suggests that both signals came from the brutal collision of two neutron stars. And again, notice how it says that the evidence suggests that both signals came from the brutal collision of two neutron stars. But I'm here to tell you guys, as a flat Earth proponent, knowing what we do know, there's no such thing as neutron stars. Stars are just lights in the sky. So if they do collide, maybe they collide. I don't know. I don't think anybody's ever witnessed stars collide with the naked eye. As far as I know, the stars in the night sky have never moved a smidgen relative to one another. So I guess we're going to have to take their word on this too. Anyway, brutal collision of two neutron stars. The double whammy makes LIGO's detection seem unequivocal. Even here, though, the Danish group is dissenting. Thank God for the Danish group. They point out that the collaboration initially registered the event as a false alarm because it coincided with what is known as a glitch. And I guess that's the technical term for it. A glitch. The detectors are plagued by these short, inexplicable bursts of noise, sometimes several every hour. They seem to be something to do with the hardware with which the interferometers are built. The suspension wires and seismic isolation devices, Cornish says that LIGO analysts eventually succeeded in removing the glitch and revealing the signal, but Jackson and his collaborators are again unconvinced by the methods used and the fact that there is no way to check them. And isn't that the thing about science? It's supposed to be repeatable and checkable. We're not just supposed to have to take some multi-billion-dollar lie factory's word for things. That's the thing about science. Whatever it is these guys are doing at LIGO, it sure as hell ain't science, I'm sorry to say. Continuing with the article, what are we to make of all this? Tons of money for LIGO, that's for sure. Nothing, apparently. The Danish analysis is just wrong, insists Cornish. Quote, there were very basic mistakes. Those mistakes boil down to decisions about how best to analyze the raw data. And see another subsection, how to catch a wave. Anyway, not everyone agrees that the Danish choices were wrong. Quote, I think their paper is a good one, and it's a shame that some of the LIGO team have been so churlish in response. By the way, churlish means rude. So they've been pretty rude about people actually questioning what they're claiming. And where's there room for that in science? I mean, isn't science supposed to welcome scrutiny? Isn't that how science progresses, is by scrutiny of peers reviewing claims and assertions made by other scientists? I mean, what are we doing here, guys? Anyway, so LIGO team have been so churlish in response, says Peter Coles, a cosmologist at Maynooth University in Ireland. Oh, I should have done his quote in Irish. Not everyone agrees the Danish choices are wrong. I think their paper is a good one, and it's a shame that some of the LIGO team have been so churlish in response, says Peter Coles, a cosmologist at Maynooth University in Ireland. McConaughey concurs. Right now, this is not the Danish group's responsibility. The ball is in LIGO's court, he says. There are questions that should be answered. Brown thinks the Danish group's analysis is wrong, but worth engaging with, and Cornish admits the scrutiny may not be a bad thing. He and his colleagues plan to put out a paper describing the detailed properties of the LIGO noise. It's the kind of paper we really didn't want to write because it's boring and we've got more exciting things to do, like finding snipes and measuring the dreams of farts and that sort of thing. But he adds, I added that bit in, by the way, that was not actually part of his quote, but he adds, it is important and increased scrutiny and criticism may be, in the end, no bad thing. You do have to understand your noise, he says. Wow. Well, at least this guy has somewhat of a brain on his head. I mean, wow. That's a surprise to me. Cole himself doesn't doubt that we have detected gravitational waves, but agrees with Jackson that this cannot be confirmed until independent scientists can check the raw data and the analysis tools. Quote, in the spirit of open science, I think LIGO should release everything needed to reproduce their results. I'll do it in Irish. Coles. In the spirit of open science, I think that LIGO should release everything needed to reproduce their results. End quote. Jackson is unconvinced that explanatory papers will ever materialize. The collaboration has promised them before, he says. This LIGO episode continues to be, quote, this LIGO episode continues to be the most shocking professional experience of my 55 years as a physicist, he says. Not everyone would agree, but for a discovery of this magnitude, trust is everything. And again, I would mention here to Jackson, I'm sure he's not listening to this, but if he ever does hear this, the reason that they are so balls to the wall with these cockamamie, willy-nilly claims without backing it up, and really I'm just going to come out and say it, lying, fudging their data, is because they did this in response to flat earthers just beating the crap out of the globe earth model and beating the crap out of the theory of gravity in general. And when it became really public knowledge to the average person out there that the theory of gravity had never been proven, LIGO sort of had to come up with something. I'm not sure who calls the shots at the upper echelons, but it seems to me that it came from the very top of Alliance that, okay, LIGO, do your stuff, guys. You have to prove gravity waves. We don't care how you do it. We don't care, how you get the snipes. Just bring 12 snipes in. Nobody bothered to ask, well, what exactly are snipes? But at least the Irish guys were like, well, you don't even know what a bloody snipe is, for Christ's sake. Embarrassing noises. In 2014, the operators at the BICEP 2 telescope made an announcement so momentous there was talk of a Nobel Prize. A year later, however, far from making their way to Stockholm for the award ceremony, they were forced to admit they had been fooled by an embarrassing noise. And again, this was a year prior to LIGO's little press conference here. And of course, these were all coinciding. I think one coincided with Einstein's birthday, and the other was 100 years after the postulation of his general theory of relativity. I don't know, but they just had to have it right on time for Einstein to be perpetually correct. By the way, this will be a good time to plug a video I did a while back. It's a pretty good one. I think you'll enjoy it. It's called Einstein's Perpetual Pedestal of Correctness. Very enlightening. Okay, so anyway. Embarrassing noises. Situated at the South Pole, BICEP 2 had been scanning the cosmic microwave background, the pattern of radiation left on the sky from light emitted soon after the Big Bang theory. The big announcement was that it had found that gravitational waves had affected the pattern in such a way that proved a core theory of cosmology. The theory in question was inflation, which says the universe went through a period of superfast growth right after the Big Bang. For almost 4 decades, it had been unproven. Now, suddenly, inflation supporters were vindicated. Okay. Just a quick point of contention here, and maybe this is too far off into the weeds, but they're talking about seeing light or radiation, a pattern of radiation, and again, this is the cosmic microwave background, pattern of radiation left on the sky from light emitted soon after the Big Bang. The Big Bang is a theory. They say happened billions, trillions of years ago or whatever. But I'm sorry to say, you guys, the Big Bang Theory is only necessary, hypothetically, if the Earth is a spinning globe in outer space. Since the Earth is not a spinning globe in outer space and is demonstrably a stationary plane, there is no need for the Big Bang Theory, so the cosmic background radiation is something else entirely, making this entire venture that they described here in this subsection null and void, moot, just nonsense. Okay. Anyway, except awkward warnings emerged within weeks, suggesting that cosmic dust clouds had scattered the radiation in a way that fooled the BICEP 2 researchers. In the end, the team's estimate of the amount of dust present and the analysis of the kind of noise the dust would produce both proved to be flawed. Noise can hoodwink even the smartest. That is why, despite LIGO being a highly respected collaboration, there is good reason to take questions about its noise analysis seriously. See the main story. Okay, so here we go with how to catch a wave. Output from gravitational wave detectors is full of noise. Disentangling the signal requires decision-making, and poor ones could be disastrously misleading. So there's guesswork involved, there's eyeballing involved, and, we're still going to get these snipes though, right guys? Going to get them. All dozen of them. The best weapon in the arsenal is known as a Fourier transform. This splits a signal into various frequency components and converts it into a power spectrum, which details how much of the signal's power is contained in each of these components. It can be done with a window function, a mathematical tool that operates on a selected part of the data. Whether or not to use one is at the heart of the disagreement over LIGO's results. See the main story. Andrew Jackson's dissenting team at the Niels Bohr Institute in Denmark chose not to use a window function, a decision that LIGO's Neil Cornish describes as a basic mistake. Jackson says they didn't use one because it subtly alters the Fourier transformed data in a way that can skew the results of subsequent processing. Makes a lot of sense. Even with the Fourier analysis done, judgments must be made about the noise in the detectors. Is it, for example, distributed in a predictable pattern equivalent to the bell-shaped Gaussian distribution? And does it vary over time, or is it stationary? The appropriate techniques for processing the data are different depending on the answers to those questions, so reliably detecting gravitational waves depends on making the right assumptions. Jackson's group says the decisions made during LIGO analysis are opaque at best and probably wrong. What a terrific article, just really well done. And honestly, I've never read much from newscientist.com, but this guy, Michael Brooks, did an excellent job of writing the article. And I must commend the guy, Andrew Jackson. Maybe it's something in the name, but it seems like this guy is, at least, his moral compass is headed in the right direction, and he does have truth as the ultimate goal of his scientific endeavors, as opposed to others. Not going to say any names, but LIGO and NASA, where basically the funding is the most important thing to them, and perpetuating the status quo paradigm is just the most important thing ever, right? I mean, that's what they must do. So that's the end of that article, and I had one or two more that I wanted to breeze through with you guys. Or did I just close the wrong one? Whoopsie. Oh, wow. I think I might have just closed the wrong one. Let's go to history here. Yes, this is the one I was looking for. Okay, so the next article we're going to look at here is from spaceplace.nasa.gov. So coming straight from the horse's mouth, the be-all, end-all source of truth, NASA. I'm kidding. I think I'm probably going to hell for saying that, so please do not take me seriously when I said that. Okay, so what is a gravitational wave? So we did talk a lot about gravitational waves and all that, and I just wanted to give a bit of a rundown. Maybe I should have read this article first, but hey, when in Rome, right? When we're trying to find snipes, we might as well start at the end and work our way back to the beginning, right? So what is a gravitational wave? The short answer, a gravitational wave is an invisible, yet incredibly fast ripple in space. So the very first sentence here on NASA.gov here, you guys, gravitational wave is theoretical. One has never been detected, measured, proven, and yet we know it's incredibly fast. That's one thing we know about something that doesn't exist. Things that don't exist are very fast, right? Okay, anyway, gravitational waves travel at the speed of light, they say, 186,000 miles per second. These waves squeeze and stretch anything in their path as they pass by, says Nasser. They squeeze and they stretch. Yeah, sure they do. A gravitational wave is an invisible yet incredibly fast ripple in space. We've known about gravitational waves for a long time. More than 100 years, a great scientist named Albert Einstein came up with many ideas about gravity and space. Wow. So we've known about gravitational waves for a long time because Albert Einstein thunk it, right? I mean, this is how science is done, right, guys? Isn't it? I mean, Albert Einstein thunk it, so therefore it must be true. I mean, that's just so typical. Again, I'm going to point you in the direction of a video I did a while back. Please do watch it if you haven't seen it. Again, it's called Einstein's Perpetual Pedestal of Correctness. Brilliant video. And I may actually have another Einstein video that I'll point you to as well. I'll put some cards in corresponding places, links in the description, and on the end screen I will try to remember to place options for you to watch these Einstein videos I keep mentioning. It is important stuff, okay? I mean, not Einstein, but just what a buffoon and just a, I would say a fraud that he was, but anyway. By the way, Albert Einstein officially, 1921, won the Nobel Prize in Physics photograph. Wow. Okay. So Einstein predicted that something special happens when two bodies, such as planets or stars, I thought it was going to say males and females, but no, planets and stars, not that juicy. When two bodies, planets and stars, orbit each other. He believed that this kind of movement could cause ripples in space. These ripples would spread out like the ripples in a pond when a stone is tossed in. Scientists call these ripples of space gravitational waves. So let me just stop the wagon here real quick, back up the wagon, you guys, because he's talking about, throwing a rock into a pond and you get ripples. We can all understand that. That makes a lot of sense. But in space, we are talking about null, void, nothing, nada, zero space. It is a lack of stuff. It is a vacuum. Okay, sure, you allegedly have stars and planets and moons and meteoroids and asteroids all throughout space, but at the end of the day, what we're talking about here is the negative space, the expanse that they claim goes on practically for infinity. So you tell me, you guys, if you throw a rock into a pond of water, it makes ripples. But if you throw a rock into a pond lacking water, a pond with nothing in it, where's the ripples? I mean, what kind of ripples are we going to make then? Huh? Well, I'll just let you be the judge on that, and I'll give you my opinion. Well, you're not going to have many ripples at all because you don't have any sort of media to house the waves. Right. Sorry, I just love doing accents sometimes when we do these sorts of videos, so forgive me. Okay, so gravitational waves are invisible, it says. However, they are incredibly fast. I think that's the third time this article has mentioned that. I'll tell you, NASA.gov, you should let me write your articles, dude. Really, is that the third time that they've said literally gravitational waves are invisible but incredibly fast? Let's see here. Okay, it says it here at the top. Gravitational wave is invisible yet incredibly fast. It says it here, gravitational wave is invisible yet incredibly fast. Okay, and then it says it down here. Gravitational waves are invisible, however, they're incredibly fast. Really, is this the best sort of articles we get from NASA.gov? With their billions and billions of dollars. Please, you guys, NASA, give me a job writing articles, or at least cleaning up your mess on your articles. I promise. I won't debunk any of your stuff if you give me creative liberties in your website. Well, I can't make any promises, but at least I can promise that the truth will be on your website. Anyways, it says here that these hypothetical, fictional, non-existing gravitational waves, which did I mention that they are invisible but incredibly fast? They travel at the speed of light, 186,000 miles per second. Gravitational waves squeeze and stretch anything in their path as they pass by. Well, where have we heard that before? What causes gravitational waves? Well, the most powerful gravitational waves, by the way, so they're telling us what causes gravitational waves. They're telling us about different types of gravitational waves. You got some less powerful, some most powerful, and yet to date, there is no evidence for gravitational waves ever to this very day. But the most powerful gravitational waves are created when objects move at very high speeds. Some examples of events that could cause a gravitational wave are when a star explodes asymmetrically, called a supernova, when two big stars orbit each other, when two black holes orbit each other and merge. Okay, so just a bunch of theoretical nonsense as far as I'm concerned. I would play this little thing here, but who wants a copyright strike, right? But you can see ripples in space. Yeah, as if, right? Let me go get my jet ski, and I'm going to put it in the air. And I'm going to gun the engine and just see how fast my jet ski goes, right? In the air, right? Go very fast, I'm sure. Anyway. But these types of objects that create gravitational waves are far away. And sometimes these events only cause small, weak gravitational waves. The waves are then very weak by the time they reach the Earth. This makes gravitational waves hard to detect. Because I gotta tell you, it's hard to be NASA. Oh yeah, hard to be NASA. And I gotta tell you, I will mention here, according to the Alliance standard model, right? We have the Earth orbiting the Sun, the Moon orbiting the Earth. We are held to the Earth by gravity, and all of this is governed by gravity. Shouldn't gravitational waves just be abound? Shouldn't they be everywhere? Shouldn't they be detectable just all over the damn place? Electromagnetic waves are detectable on any scale. Small scale, micro scale, macro scale. Electromagnetic waves and effects are demonstrable, detectable. I wouldn't maybe say tangible, but it's something that we know exists, and there's no doubt about it. Now, the inner workings of exactly what's going on in sort of electrical systems or electromagnetic systems, that's a horse of a different color. But we do know that it is a thing, right? It's definitely a phenomenon. Gravity, not so much. So they say that this makes gravitational waves hard to detect, the fact that it's weak and far away objects. But I would say what makes gravitational waves even harder to detect is that the damn things don't exist. And here we go. How do we know that gravitational waves exist? In 2015, scientists detected gravitational waves for the very first time. They used a very sensitive instrument called LIGO, Laser Interferometer Gravitational Wave Observatory. These first gravitational waves happened when two black holes crashed into one another. The collision happened 1.3 billion years ago, but the ripples didn't make it to Earth until 2015. Now, I know we've just discussed all of this, So NASA.gov leaves up on their webpage, and again, the date today is we're July 30th, July 31st of 2021. This is 6 years old. It was debunked by mainstream science, peer-reviewed guys, not flat earthers, but debunked by their own guys, some of the boys, years ago, and yet NASA is still has this stuff posted up as being proven, so that, well, this is why, I'll tell you why. When flat earthers make the bold claim that gravity is a theory that's never been proven, well, the globetrotters can go to web pages like this here. See, it says NASA.gov, and here it says right here, we do have proof of gravity waves. That's why. And, who cares if this stuff is, you could say it's being debated by scientists, but no, it's been debunked. I mean, even mainstream scientists that don't have their heads up their buttholes say that it's basically a bunch of malarkey, right? Like Andrew Jackson, okay? And I'm just out of curiosity, I do want to see, when was this article published? Does it say? Who cares anyway? But the point is, they still have it up. It's not like they took it down. You'd think that NASA would take this sort of thing down, right? And here's a nice picture of LIGO, the multi-billion-dollar lie factory, NASA's El Cheapo cousin, right? And here we go, back to Einstein's perpetual pedestal of correctness. Einstein was right, of course he was, because Einstein can never be wrong, because he's Einstein, and whatever he thunk is true, no matter what, and we will spend the rest of our lives trying to prove him right, proving him right, even if his claims are just malarkey, hogwash, couldn't possibly be true. For some reason, he just is forever correct. I mean, he gets a free pass when it comes to science or liance or pseudoscience because, well, with a name like Einstein, how could you be wrong, right? I mean, that's pretty damn good science. His name's Einstein. So, hey, and he invented a bra. Yeah, look it up. See my other videos I've mentioned. Okay, so the first detection of gravitational waves was a very important event in science. Before this, just about everything we knew about the universe came from studying waves of light. Now, we have a new way to learn about the universe, by studying waves of gravity. Or, wait a minute, does it say by studying waves of naivete? That's what it is, by studying waves of naivete. Great. Gravitational waves will help us to learn many new things about our universe. We also may learn more about the galaxy, about gravity itself. Really? So by studying gravitational waves, we might learn more about gravity. Well, that is just profound writing. We ought to give this, who are these guys? NASA? We ought to just dump billions of dollars at these guys, because I'll tell you what, their websites, their articles are just profound, man. Profound science right here, you guys. And how are gravitational waves detected? And it goes on to tell you about LIGO. We know all about that. We've been through it ad nauseum in this video. So, yeah, catch a wave. Looks like we've got that done. LIGO, what are gravitational waves? Yeah, so, and this is the final article I was going to read. It may not be necessary, but I think that it is, just for a bit of background. And again, this is caltech.edu. So again, mainstream. These are not flat Earth sources that I'm citing here. These are mainstream. LIGO.caltech.edu. Okay. What are gravitational waves? Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe. Albert Einstein, you guys ever heard of him? Albert Einstein. He predicted the existence of gravitational waves in 1916, so they must be true. No, in 1916, in his general theory of relativity, Einstein's mathematics showed that massive accelerating objects such as neutron stars or black holes orbiting each other would disrupt space-time, a theory, in such a way that waves of undulating space-time would propagate in all directions away from the source. These cosmic ripples would travel at the speed of light carrying with them information about their origins, as well as clues about the nature of gravity itself. Wow, I wonder what kind of clues. Clues like gravity doesn't exist, couldn't possibly exist, has no theoretical need to exist because the Earth is not a spinning ball. This all comes back to curvature, you guys. This all comes back to lack of geological motion. If there is no geological motion, no axial rotation, no orbital motion of every sort, if there is no curvature to the Earth sufficient to result in an overall sphere, then the Earth cannot be a spinning ball, and therefore all of the theories of Big Bang and gravity universe are just completely useless. There is no potential need for them. Okay? The strongest gravitational waves are produced by cataclysmic events such as colliding black holes, supernova, massive stars exploding at the end of their lifetimes, and colliding neutron stars. Other waves are predicted to be caused by the rotation of neutron stars that are not perfect spheres, and possibly even the remnants of gravitational radiation created by the Big Bang. The animation below illustrates how gravitational waves are emitted by two neutron stars as they orbit each other and then coalesce.